Okay, welcome to our review for the MCAS as far as kinetic energy and potential energy, everything you need to know to do well on the MCAS. So here are a few notes of things that you should know about potential and kinetic energy. Potential energy is the energy of position, and particularly the MCAS cares about what we call gravitational potential energy, which is the energy basically of how high something is. As you lift something up, you give it more potential energy, and you could try that. You could lift like a book or a notebook and then drop it, and you'll notice the higher you lift it, when you let go, the louder the sound it makes when it hits the ground. That's because you stored up more potential energy. This is stored energy. It has potential to do something. This is stored energy. So it is the mass. You see this formula from your formula sheet. The letter M for mass, the letter G for gravity, and H, or on your formula sheet it might have delta H for change in height. And you could easily look this up on your formula sheet and know what potential energy is all about. Gravitational potential energy. Again, G is in the lower left corner of your formula sheet, gravity on Earth being 10 meters per second squared. And then kinetic energy is the energy of motion, particularly how fast something's going. You see this lowercase v here, velocity squared. So that makes a big difference. Whenever you square a number, it makes a big difference in the answer you get here for kinetic energy. So half of the mass, 1/2 the mass multiplied by the velocity squared will give you your kinetic energy. It's the energy of motion. So something that's moving faster has more kinetic energy. Obviously something more mass, because mass is part of this formula, has more kinetic energy as well. And energy is conserved. This is called the law of conservation of energy. So that means that energy is not created, energy is not destroyed, it just changes forms. So whatever amount of energy you start with, you're going to end up with the same amount of energy at the end. It just may have changed forms. So maybe as a roller coaster goes down a hill, some of that potential energy it had at the top of the hill turns to kinetic, but you may notice not all of it, because you may have lost, quote unquote, lost some energy to friction, which basically, that friction created heat, thermal energy, or air resistance, or whatever. So it's not that you're losing energy, it's just that energy changed form. So not all of the potential changed to kinetic. It may have went to some thermal, some heat energy. But if you add it all up, in the end, you'll get the same amount of energy. So we have energy changing forms, and MCAS really talks about potential change in kinetic, or even doing work, lifting the object, doing work to it, force times distance. That work creates potential energy, which then, if the object falls, converts into kinetic energy. So these are the main ideas, main things to get in your notes about potential and kinetic energy. Here's an example problem. So we have 3 boxes lifted to different heights. They give us the weight. Now, notice it's not kilograms here. If the box was in kg, they gave us mass, kilograms, we'd have to multiply it by gravity before we multiply by the height to get the potential energy. But they already did the mg for us. They gave us the weight of each box. So the mass times gravity is already done. So this is actually a little bit easier of a calculation here. All right, we're trying to find which best describes a box's change in mechanical energy. All right, so mechanical energy is either potential or kinetic. It's basically the total of these types of energies. Mechanical energy is just a general term for that. So we're lifting boxes. We're doing work to these boxes. So as we lift them, as we saw, potential energy has to do with position, the height. So we're going to use the potential energy equation to solve for the mechanical energy of these boxes. So we know the formula, and they already did the mass times gravity, as I mentioned, because they give us the newtons, the weight. So we're just going to multiply by h, the height. So we have these boxes here, and we have the potential energy of box X, potential energy of box Y, and potential energy of box Z. So how do we find that? Well, again, we have the mass times gravity. Now we multiply that by h, the height, to get the potential energy. And we'll find out which has the greatest amount of mechanical energy. So you actually have to do the calculations for each of these to basically see which of these statements would be correct. Did X have the greatest change? Did Z have the smallest change? Did X and Y have the same? Did Y and Z have the same? So as you look at the calculations below, you'll see that Z had the smallest change. 1,525 is the smallest amount. And again, I didn't mention this earlier, but I should mention J for joules is the unit for energy as well as the unit for work. Number 2, we have a 9 kilogram model airplane flying horizontally at a constant speed. If the plane suddenly dives from its altitude of 50 meters and levels off at 20, how much potential energy did it lose in the dive? So we're trying to figure out potential energy once again. So there's a few ways to do this. We could figure out the potential energy it had at 50 meters and the potential energy it had at 20 and subtract to see how much potential energy it lost. So typically what I'll do is I'll have two people come up. One will calculate PE before, one will calculate the potential energy after. So why don't you go ahead and figure out the potential energy it had before and after. Now another way you could do this is on the formula sheet you'll see the potential energy is mass times gravity times delta H, change in height. So what you could actually do is take the 50 and minus the 20 and figure out, oh, it changed by a height of 30, and just use that 30 meters, and that would be your height. So you'd multiply the mass, the kilograms, don't forget to multiply gravity, which is 10, and then multiply by the change of height, which is 30. And that's how you'll get your answer. Mass, 9 kilograms, gravity, which you find at the bottom of your formula sheet, 10 meters per second squared, and height. And then your formula sheet has triangle H, delta H, that means change in height. So finding the change between 50 and 20, well, that's a change of 30. So when you multiply that all together, you'll know which of these is the correct answer. I'm not going to tell you because I want you to actually try it, but you should know when you multiply it that you'll find the correct answer for that one. Okay, a cart at the top of the hill is released and rolls down the hill. Which of the following describes the energy of the cart as it reaches the bottom? So think about this. Okay, at the top we have potential energy, right? It's about height. Now as it's rolling, that potential energy is changing into the energy of motion, kinetic energy. So A says the cart has no energy. No, that's not true, right? Because the cart's moving, so it has kinetic energy, right? Now, I skipped over B because I think those of you who've been following along understand that, well, at the bottom it's going to have maximum kinetic energy because it's moving the fastest. So I want to show you why these other answers aren't good first before we talk about B being correct. So C, the cart has maximum gravitational potential energy. That's true at the top of the hill, not the bottom. It's at the lowest, so it has no potential energy. All right, it has equal gravitational kinetic. If it has no potential energy, then potential energy and kinetic energy cannot be equal, right? Because at the bottom, all the potential energy is zero because it changed into kinetic energy. It's going the fastest at the bottom of the hill. All the potential has changed to kinetic. So this is a very common type question you'll see in the MCAS talking about the transformation of potential into kinetic energy. Which of the following increases when a metal spring stretched horizontally? Now you will come across some MCAS questions that aren't necessarily about gravitational potential energy, the energy of height, but more about potential energy in a spring or an elastic. So these are all forms of potential energy, which is stored energy, the energy that's stored. It has potential to do something. So if they're talking about stretching the spring and they didn't let go, that spring has tension. It has some energy stored up into it. Okay? So this is a form of potential energy. Whenever you're pulling an elastic or pulling a spring, you are stretching that and you're storing energy within there, giving it potential to do something. This is potential energy. If I let go, you know the rubber band or the spring would go flying and that potential would change into kinetic. But as long as you're stretching and holding it, that's potential energy. Okay, we have a pendulum in motion. So a pendulum is simply something that's swinging back and forth, kind of in this simple harmonic motion where something's just swinging back and forth here. And a pendulum's a great example of potential turning into kinetic, okay? Because at the top, this is gaining height, so we have potential. As it swings down, it's losing height, but it's also going faster as it swings. At the bottom, it's going to be moving the fastest. Its potential turned into kinetic. Then as it starts to go up, it starts to slow down. Gravity's pulling it down. It starts to slow down. So it has less kinetic, but it's turning back into potential. So we have potential to kinetic, back to potential, back to kinetic, over and over and over again. So we're talking about what happens to the pendulum's gravitational potential energy at point P. Well, we're changing back and forth between potential and kinetic, and at P, at the very bottom, all this potential energy stored due to the height has changed into kinetic as it's moving the fastest at the lowest point at point P. So using what we learned, we can answer this next question. Here we have a sled going down a hill, starting at W, a high point, coming down this little dip, up another hill, and then to Z. So it's frictionless, so we're not losing energy to friction. And it goes past point Z, what best describes the energy of the student from W to Z. So hopefully thinking about the pendulum and how energy is conserved. We're changing energy, but the total amount of energy stays the same. So all the potential energy at W, because of its height, will become kinetic energy at Z. Should be moving very fast now because all the energy transformed. So the potential energy at point W becomes kinetic energy at Z. So we have a man swinging golf clubs here in this question. So we want to know what best explains why it says here the kinetic energy at Y is more potential, and how does this not violate the law of conservation of energy? Because remember, the energy you start with should equal the exact same amount of energy at the end. So if this has more kinetic energy than it had potential at X, there must be a reason why. So what's the reason? What's going on here? Well, this is some guy swinging this, so he's probably adding some energy. He's using his muscles to add some energy to this. That's the only reason why it would have more energy at the end. Energy must have been added to that golf club as he swung it. He's putting some of his own energy into that. Okay, so this basically concludes our little video summary here of the potential and kinetic energy for the MCAS. So now you're going to use that information to look at some questions, some open response, and good luck.